My name is Fukami. I work for a web application security company in Cologne called Section 1. And I started to look at Flash like 1.5 years ago when I had to order some Flash for a client and didn't know how to do that. And it turned out to be like a very interesting topic. This is Bev. He's the author of AS2, which is a very, very cool Erlang-based Flash decompiler, and it does lots of more fancy stuff, but he will explain later. And in case you have some trouble compiling it on Windows, he even didn't get it, so you have to complain at him. So what's our agenda? We got some malware samples so that we could do some statistics on how good is that tool for especially to generically detect attacks or like malware stuff. Then we will talk a bit about the file format itself and ActionScript, the ActionScript bytecode stuff. Then we will also talk about some analysis methods. It's basically about static analysis of Flash files, some obfuscation techniques, some which are well known and some which are not that well known. And yeah, we have a couple of ideas we also want to share with you. So I just want to start with some shout-outs because Flash is a quite like prominent technology since like 80% or more browsers in the world carry that plugin, and there are not that much people doing work on it. So shout out to Nicholas Canas. He's a guy who actually is the author of Hacks. It's mine. Nicht jetzt, okay? Hex is a wonderful compiler for like compiling all types of Flash, like in all versions, and even you're even able to do stuff you are not able to do with Adobe stuff. Then Mark Dowd, he wrote this wonderful paper about Flash, like attacking the ActionScript's VM. Really, you have to read that one. Then thank you, Ben. I hope he's here. I think he just pointed me or pointed us at some thing we already developed, but didn't really recognize what we'd done. So it was very, very cool, like from him to tell us. Then Stefano Di Paola, he's a guy who did some nice tool called Swift Intruder, and he was also actually one of the first guys who really briefly looked into Flash and found some very interesting vulnerabilities. Yeah, and last but not least, Hossein Azari, who provided us with like 3,500 samples of Flash, which were used in attacks. So it was very, very useful for us to have this material, because before we had like 10 or so, and that was really, really nice. So the main idea is how far can we play the obfuscation, de-obfuscation game. So why actually we are thinking about it? I mean, like the basic idea was to have a generic way to like looking for something to like carry and exploit and have it in a way that it's hard to detect and it's hard to analyze on one hand, and on the other hand, really looking at how far can it go, like with de-obfuscating all the stuff and just understand what's really going on inside the VMs. And also what possibilities are there for filtering Flash at like the perimeter or the clients itself, so that people who need need to use, for some reasons, this plugin gets at least some protection, or people who are not using NoScript or other stuff are having protection as well. So we are focusing a little bit on like lesser known obfuscation techniques, which is basically only available in ActionScript 3. Yeah, and Beth will briefly explain that. As I said, we don't want to talk much about attacks, but these are some generic attacks which where Flash just played a role in one way or another. I mean, like most of the files we saw were really like banner ads, which were used to like simply redirecting the client, and that's it. It's basically like 80% of all or more of all Flash files we have. They are very, very simple in the way they do they're used in an attack. But there's a lot of stuff possible, like for example DOM injections, and like it's really a way to like remote controlling the client. And there are also attacks possible against the VM itself, like Mark described in the paper, and also against the analysis tools. There are a couple of tools which really have problems, like malformed Swift, and yeah. So this is basically the attack surface we have. When you are thinking about having a Flash file, executing something, that's basically that's a like perfect possibility in terms of that means full access to like the DOM and like ejecting everything what you want. Most attacks are much simpler. They don't use that one. They just use like a simple redirect. This external interface call is actually JavaScript either, so that's like full access to the client, and it works on same domain by default. Okay. Yeah, and it's same domain by default means like if you are able to run that code on a client, you have full control over the domain where it's loaded from. And this example can be easily compiled to ActionScript 2 or 3. So one idea of us was there are a couple of like vulnerabilities in ActionScript 2 and 3, or like abilities you would like to use in certain attacks. So we were looking for a way where you can like carrying all types of exploits and using like ActionScript 3 as a loader for it. Why people are actually thinking about obfuscation? There are a couple of like use cases for obfuscating Flash. The simplest one is like developers want to protect their IP, so that now other developers or designers can steal their stuff. So it's not that it's only like used in attacks. The other, or the second use case is like using it in mass exploits, for example through banners or wherever you are able to like present Flash to some users, and the main like people who need to know about Flash being malware or not is like the publisher and content providers and like ad networks who like deploy those stuff. Then there are soft targets, means like companies or so which don't fully monitor the traffic, for example. So there is a good chance to like crafting an exploit and get it to run, and nobody is really actually able to like able to find out what actually happened. So the people who need to know about this Flash stuff is like administrators and security officers in like companies. And then there are the hard target. This means like a target which monitors everything, so that you need some sort of side channel to like encrypt the exploit. Yeah, and this is actually something. What we found out is like if you capture all traffic and if you then there's a good chance that you are able to like understand how the attack works. If you don't do the whole network capture, it's basically possible to like crafting exploits that are not really reversible anymore, or not that easy at least. So we just looked at 100,020 flash files. That's like an overview of our versions, like Swift versions and ActionScript versions. These are basically like, it's like everything which is used in most cases, but the most interesting thing was how much is really like ActionScript 3 based flash, and it's not that much. But that's actually the interesting part for us to look at, because they're much more interesting like thing to do with ActionScript 3 than with ActionScript 2. So Earl Swift has a couple of checks. So we checked like all of these files, and these checks are really, really simple. They check for, what was it, like branch offset. Anyone else?
Yeah,
So,
I'll go into detail later.
Okay. So the interesting thing is that from the 3,512 known flash files we used or were used in attacks, there were only like 31 were not detected. So it is a quite nice like thing with like only 2 checks. But as I said, most of them are really, really simple. So yeah, but you also had a couple of false positives, and there were a couple of like, we actually have to look at some of those because there were actually some weird errors. Yeah, and now I hand over to Bev because he is like briefly explaining you the file format itself and stuff.
Oh, thank you. So this microphone actually on? Okay. I will now explain to you a little bit about the Swift format itself. In order to understand the analysis which we have done so far, first of all we have to know the format, which basically is a container format, just like a jar file, for example, you might know, or a zip file, or just any other container format. It contains, well, it starts with a header, with the size of the flash file, and then a few attributes, then a tag, another tag, and another tag, many other tags, finally an end tag. That's basically it. So each and every tag can contain arbitrary data. For example, a constant pool, you might need constants for some reason, then media, images, they can contain fonts, they could contain audio files, they can contain whichever you like, which mostly be like audio video font thing. And of course, most importantly, actions, which is bytecode as defined by do-abc, which is listed here, a do-action. The tags itself contain like kind of sub-tags, which are called actions for do-action. Starts with a little header, and then you've got action, another action, which is the actual bytecode. So for ActionScript 3, you've got a completely different set of actions, which is do ABC. It looks totally, well, not too far apart actually, but it's totally different. And we'll go into detail later on. Another example of another tag would be an actual action, which is the get URL thing, which is, well, it's an example. It has a header, a length, URL, target string, so it gathers the data behind the URL. Now, you might wonder, the Flash player actually has not only one virtual machine, but 2 entirely different virtual machines built into it. Start from version 9, you've got a second virtual machine. And there are not so many parsers available to parse bytecode, partially because of that. That's a brief excerpt from the manual. It says, section primitive data types. Here, the variable length encoding for unsigned 30-bit uses 1 to 5 bytes. If the high bit of bytes is set, then the next byte is also part of the value. So you've got expanding bytes. It goes on like that throughout the manual, which is, it's not really difficult to understand after all. It's not difficult to implement, but it's, well, it's slow to implement, if you know what I mean. Then there is a very important function or functionality, which is a load bytes functionality starting from flash 9, which is a load bytes. It's possible to load arbitrary bytes from external sources, from internal sources, packed into the flash file and modified any way you like, byte-wise, and then load it into the interpreter. And that's basically a very, very neat way to implement obfuscation techniques. We'll talk about that later on. But first of all, our main objective would be to analyze flash files. You've now seen approximately what the Swift container format looks like, so I'll go to the analysis. The very obvious method to use for analyzing a flash file would be to just run it. You start the player, you run it. Has anyone actually switched off Flash in the browser here? Please raise your hand. Oh, it's like everybody. Okay, has anyone left it switched on? It's, okay, like a third maybe. Okay, each and every time you run the Flash file, you're basically doing a runtime analysis, even if you're not actually analyzing it. But, well, usually you would do that in a very contained environment where you can see how it's actually working. But we'd like to prevent that in the first place and know what we're executing, so we try to stick to static analysis here. And the very obvious pattern matching method is what's approximately like the data definition for virus scanners looks like. You know what might be a malware or a flash file you don't want to execute in your browser, so you're searching for patterns that you know in advance. You could also check for strings in URLs, strings in constants, or inconsistencies. For example, there is the data type of a string in Flash, and the string may be null terminated, and in addition have a length value associated. They might not match, so that would be an inconsistency. Or you've got an end tag where the Flash file is supposed to end, but there might be arbitrary data behind there. It's another inconsistency, and we can search for that. It's a very simple pattern matching. However, when designing your payload or trying to hide your payload, you might know that we're searching for these anomalies and just not use them. So the next obvious choice for an analysis method would be a statistical approach. Here we go. So, like most statistical approaches, it's not really difficult math. It's mostly about counting things. You can count functions, for example. You could count the occurrence of functions and compare it to a reference set. Or you can count the tags and compare it to tags usually being used in your reference set. And then get an approximation to what might be worth executing and what might not be worth executing. Of course, not 100%, it's always like a spam filter. You might get lucky or not. Of course, it's possible to analyze constant names. For example, the constant name next ID or variable name next ID is much less likely to arise suspicion than something else. Of course, in order to apply statistical methods, we need lots of Swift files to analyze as a reference set. So, the method we chose in this particular instance is a statistical classification for ABC bytecode, which is basically based on n-grams. Has anyone heard about n-grams? It's a very, very common technique. I'll explain it anyway. If you've got a set, for example, the most common application would be a language detection. You've got a text, which happens to be test text here, and the n-gram with n equals 3. So we've got sets TES, EST, ST, blank, blank TE, and so on, and you count the occurrence of each group. The occurrence of each group here is 1, which is very simple. Now, applied to opcodes, that would mean, for example, you've got opcodes push, push, at, return, n equals 3, so you've got two groups, push, push, at, return. Each occurs 1 time. Normally, you would have a lot more opcodes, so the statistics wouldn't be that simple. As a matter of fact, it's not even possible to apply statistical classification properly on very, very few data. So, what exactly would be contained in n-grams of opcodes? And we thought about that a bit, read a few papers. Very interesting read is Supporting the Cybercrime Investigation Process, Effective Discrimination of Source Code Authors Based on Byte-Level Information, which happens to be a paper. And they are describing this n-gram statistical classification method for other languages, not for Flash specifically, but it can, of course, be applied. And the information included here is information about the IDE. You can gather information about the compiler, standard libraries being used, and of course, as each programmer has their own methodology or way of programming, you get information about the author or authors. This very simple graph shows statistical profiles created by the n-gram statistical classification. Each node is one profile, and it shows the distance between Swift files based on the statistical classification method. And as you can see, two groups cluster, 1, 2, and a little group down there. So we can assume that these are somewhat related based on the opcode n-grams. Are there any questions so far? Yes, please.
Maybe I missed it, but what is the exact classification method that you're using there? Just the n-grams and...
Yep. As a matter of fact, it's only... I'm creating... What I'm creating here is... Sorry?
Repeat the question. What is the metric?
Yeah, what is the metric? The question is, what is the metric? Or the method? And we're generating the profiles, n-gram profiles, from Flash opcodes, and then compare it to each other. The exact method is described in the proceedings paper. So if you're searching for a mathematical formula, it's written in there. It's also the very same formula used in this paper referenced. So what we get in the end is an approximation which flash file might be related to other flash files. So, for example, if we had a reference set, the reference set is all these, but not this one, and we'd be analyzing this particular flash file, we would associate it with this cluster, not the other one. It's as easy as that. And one cluster means it's more likely to be of like the reference set, and a different cluster means, well, it's less likely to be like the reference set. Of course, it's not 100% foolproof, and that's what we're trying to prove now. Well, first of all, the classification method can mostly be used only for ActionScript 3 based files. But I'll present a brief history of obfuscation based on ActionScript 2 as well. So when you look at it, you can read the variable a, second line, adds up to a function name, which is load vars, and the function name is being interpreted as the real function name. So when analyzing bytecode, it's not easy to use pattern matching for load vars, because you don't know that it's going to be load vars in the end. So that's a very, very common obfuscation method for ActionScript 2 based flash. Another very common method is what we call a branch offset obfuscation. You've got at least 2 tags in the Swift file. The first tag has an unknown header, so we don't really know what it is, or it could have a header for a JPEG image and just arbitrary data. But as a matter of fact, there is our secret code embedded in here. And then we've got a do action tag, which is supposed to be real bytecode and just jumps out of the tag somewhere else. Very simple obfuscation. And when you try to analyze it with a common analysis tool like Flare, you end up with this, which is basically garbage. But you can see that it's being obfuscated because it looks a little odd. Then, when we're trying to obfuscate ActionScript 3 so that it cannot be detected even by our classification method described earlier, the very first idea that comes to mind is we just take our payload, which is called NTU here, and we embed it into another flash file so that most analysis tools would not recognize it as valid Swift in the first place. But it's very, very easily detectable, and it's being loaded during runtime into the byte array here, the NTU byte array. Unfortunately, it is detectable very, very easily, but the byte array idea gets to the next step, and the next step would be this example. The code is written in hex code. Hex is an open source Flash compiler. So the whole process here would be to take our payload, we may even encrypt the payload and then encode it into a byte array, which is being loaded as another class in the data here, which is red. So we iterate over the data, and during runtime, we can decode it, or de-obfuscate, or decrypt it even, or implement whatever algorithm we like, which happens to be -1 here in the example. And then we can load our bytes and execute it. Goodbye. There are a few different types of data to hide. First of all, we may have a particular payload to hide. Then we need to hide our encryption algorithm, which could be arbitrary, and we need to hide our encryption key, of course. And we need to hide our encoding algorithm, which is totally different to an encryption algorithm, and parameters may be provided to the encoding algorithm. And of course, in the end, we end up with a line in the bytecode which says we load bytes. So the byte loading function cannot be hidden easily, which is unfortunate, but there are legitimate uses for the byte loader function, so we don't actually need to hide it. There are many places to hide. The obvious choice would be to hide it in external resources like Flickr images, or, well, there might be data hidden even in this very image, which can be extrapolated during runtime using the bytecode transformation. Tja. So the tool we've written originally focused on Swift versions up to 8, which only handles ActionScript 2 bytecode, so we implemented the pattern matching described earlier, which is very similar to virus pattern matching. And, well, recently I added ABC bytecode parsing to the tool, so the statistical classification method was able to be implemented. So what else can I say here? Well, you might like to take a look at this particular tool. It has a JSON export, it has, of course, the n-gram analysis implemented, it's got an API, and can be used as a library. And the thing here is, I'd like to present a few ideas we have, which are called random ideas. As a matter of fact, most of the ideas originated from earlier talks at different conferences like DeepSec and another conference in Belgium, where people were asking questions or having ideas about where data could be hidden, how to analyze Swift files. So the very first be we could build an interpreter in ActionScript 3 and hide the code to be executed, matching exactly the statistical profile that we calculated earlier with the n-gram method. So the bytecode being loaded during runtime would look exactly like the code of the profile, of the reference profile. Then, of course, we can try to avoid detection by exposing only strings to the constant pool that look exactly like ordinary strings. Like shown before, we can call our variables next ID or ABC, but not AX2318. That would look very suspicious. Then, and that's a very interesting point, we can use conditions set by the browser in order to have an encryption key for a very particular set of targets. For example, if you've got a browser version or a browser string, and you've got a date and time, and you've got an IP address, the DNS name, referrer, a player version, maybe even a time frame in a movie being played. So you can extract all the information, build an encryption key, and use the encryption key to target only platforms which can generate the right encryption key. Then it is possible to use a dynamic tracing by overloading, well, the class, which is displayed here, flash display loader, which happens to include the load bytes method. And the load bytes method is being used to load arbitrary data, as shown before here. Here is load bytes, so it's possible to overload the class that uses load bytes in order to like briefly check what we're actually loading after it's being decrypted. Right, more ideas. Well, actually, it's his idea. It would be nice to have a toolkit to like have an easy obfuscation, automated obfuscation maybe for payloads. Then recently, just like 5 or 6 weeks ago, Adobe released a tool called Alchemy. Now the Alchemy tool, which is based on the AVM tool, the second virtual machine, happens to implement very, very fast memory operations on byte arrays. So if we try to decrypt or decode our payload in real time, that'd be really, really fast using the new methods described or implemented in the new Alchemy tool. Well, basically it's a compiler or a compiler extension. Then we can really look forward to the Flash Player 10, which is out already, but it may implement UDP or P2P functionality. Will there be any questions so far? No questions? Yep. So, I'll briefly show you the graph again.
Here's the question.
Oh, yes, please.
I saw that code, that with the headline. I don't quite get it. Where did the actual data get into the code? Is it supposed to actually work, or is it just an example?
Could you repeat the question, please?
Okay, that's scaped. The one with the head part in it. I don't get how the data actually gets from A to the loader. It doesn't seem to have any place that it actually moves. It just seems to be an empty array.
Unfortunately, I'm unable to correctly recognize the question here. So, well, I'm not quite sure what you're referring to, but as you can see, my statistical profiles actually contain real data. They're not empty, and they're being calculated properly, so you can calculate distances between Swift files statistically. I'm not quite sure if that answers the question, but well, we're not dealing with empty arrays at any point.
What did you mean? I mean, like you were referring to some code you saw? Which one was it? Like, do you mean that one?
Move on.
Or do you mean like that?
The loader part.
That?
Later. Load bytes part.
Das kein Code mehr.
There's no code anymore. I mean, like, that's the only two parts where we show codes, like that one and...
Well, the code might have been obfuscated already.
Come on.
So we actually don't get the question?
That one.
This one?
Yeah, to me it looks like the data doesn't seem to actually be anything.
Well, you're actually right. The data is not listed here. It's being prepared externally and loaded into the compiler during compile time. So it's linked to the Flash file, but this part has been omitted.
Ah.
Yeah, but well... yeah. Well, the data, as a matter of course, it's printed in red because it's not written on the slide. It's been prepared externally, which happens to be encrypted and encoded code as a byte array. All right. Are there any more questions? Yes, please.
The random ideas, so are these ideas just how to, I don't know.
Hello? Please wait for the microphone.
Doing malware or...
Please wait for the microphone.
Well, the question is, are the random ideas, can they be used in order to obfuscate the code, if I understand you correctly, or more like to detect malware? Well,
As I said at the beginning, it's some sort of game. And so we have the possibility to like obfuscate stuff, to de-obfuscate stuff, and you want to know. Sorry? So it's a game to. Sorry? Okay. It's a game just for like, like sometimes you just want to have the possibility to detect that. Sometimes you just want to have the possibility to just hide it. So that's the basic thing. So if you do some, for example, pen test or whatever, where you think you would like to use Flash in the way that nobody's easy like detecting, or if you really want to attack someone or whatever, there are lots of uses for both sides, in my point of view. So the random ideas,
yep.
Especially, I mean, like one of the most interesting stuff, in my point of view, is like the whole like UDP stuff. I mean, like actually, the possibility to have like peer-to-peer functionality inside a browser is like amazing, And that, like, no matter what, I'm quite sure that Flash will, like, continue to be one of the major, like, sources for supplying, like, exploits, like technology which will be used for planning exploits and stuff. So that's basically ideas, just play with it and just find out about it and just get detected in some ways and stuff like that. So it's like random ideas, And on some parts we're already working, on some parts we didn't do anything, but we're just discussing it with some guys. For example, the idea of overwriting the byte loader functionality to just actually trace what's happening in the player, like getting a controlled execution of Flash. That's something which is really, really missing. Yeah? There's nothing like that, at least not available for public use.
If I could just interject for a moment. Everybody on this side of the room, if you could please keep your conversations down so that the people in the front of the room can hear and participate. And if you do decide to leave, please leave as quietly as possible. If you see a bottle, take that with you. Thank you.
Okay, are there any more questions?
Yep. Did you think of using the statistical approach to distinct perhaps ads from regular Swift files? So you can...
That actually works quite well for like banner ads, for example. Or what you mean?
Yeah, banner ads.
I mean, like, what I wanted to show was like this one thing showing the versions, for example. Yep. That's the reality of Flash out there. So most of the files are like ActionScript 2, and most ad files are like something like Swift version 6 with like some very, very basic redirect. And but the main problem is that sometimes those banner ads look like malware because they are just redirects. If you click on it, you get redirected to another domain or to another like location.
Yeah,
but
hello? Can I have the microphone switched on, please? Okay. Unfortunately, Flash banner ads mostly are Flash lower or equal to version 8. And we're trying to analyze this part here, this tiny part, which is ActionScript 3 or more. And in order to apply the statistical classification, you need data, lots of data, and there is not much data in there. It's possible to use statistical classification as well for ActionScript 2, but you need lots of data, lots of code. There is no code there. So it's not possible to apply it.
So there are other methods which are quite better to use for analysis than that for like those simple banner ads. But I mean, like Earthswift is actually able to decompile both, so that you can use it for like giving it a file handle and getting back a JSON structure of the tags and of the like opcodes and stuff. So yeah, basically we found some stuff like that in like comparing like banner ads and other stuff, and it figured out like the rogue banners, so it worked.
Yeah, for example, if you have a look at the file structure again, what you encountered during analyzing like obfuscated flash files is we've got an end tag. We encountered flashes which have not only one end tag but like 100,000 end tags. Or we found flash files that have a little clue built into the zlib mechanism, the compression mechanism, so that uncompressed data leads to endless zeros, or gigabytes even. Well, any more questions? Yes, please.
Please wait. Please wait for the microphone. Yep.
Here it is. Well, okay, the question is, what's the difference between the three classes in the diagram? And, well, first of all, thank you for the question, because as a matter of fact, comparing profiles to each other would lead to a graph connecting each and every node with every other node, and we introduced a threshold so that distances over the threshold are not being shown here. And that leads to clustering. So we just introduce a threshold, a distance threshold, and omit edges. Does that answer the question? Okay. Any more ideas? Has anyone actually ever tried to use Flash for attacks? Many, all right. Okay, thank you very much so far. If you happen to have any malware Flash files lying on your hard drives, please don't hesitate to contact us. And you might also be interested in the paper we wrote for the proceedings. So thank you very much.